Welcome, everybody, be it morning, evening, or afternoon, depending on what part of the world you're calling in from. My name is Ron Lowry. I'm the Eastern Area Manager for Hazard Control Technologies. I'm an encapsulator specialist and also a firefighter. I've got 37 years in the fire service. I currently serve as a fire chief for a volunteer department in Allegheny County, Pennsylvania. So I not only sell the product, my department, I'm a user of the product. My department's been using F500 for a number of years before I even started working for the company. So it's definitely something. I'm not just a salesman. I'm an end user as well, just like some of the folks that are on the webinar today, as well as folks just calling in to get a little bit of better education. So what we're going to talk about today is encapsulator technology, and we'll kind of go through various classes of fires and showing how you can actually expand your capabilities, make fire scenes for the municipal fire service safer for your members, and hopefully help your department to become more efficient, being able to do more with less, which is kind of one of the things I think the fire service currently is tasked to do. We're limited resources, but we're still expected to do everything we've done in the past. So kind of the theme for today's webinar, expanding your capabilities with encapsulator technology, particularly in the fire service applications. So what we're here to talk about today is what is an encapsulator agent. So we'll start with that basic definition. It's a water additive whose basic building block is a spherical micelle. Those micelles are capable of encapsulating both carbon and hydrocarbon molecules, both polar and nonpolar, on a chemical molecular level, sealing that hydrocarbon off from the oxygen on a chemical molecular bond. Kind of covers Class B fuels, but on Class A fuels, we all know that fuels burn, that Class A material burns through pyrolysis, that it's actually not the solid burning, it's off-gassing. And with an encapsulator agent, you actually have the ability to encapsulate that vapor state of that flammable vapor that's escaping off of that Class A material. So we can encapsulate in both the liquid and the vapor state. So what is F500? It's a fluorine-free, non-corrosive, biodegradable encapsulating agent. The agent's is UL listed for Class A and Class B fire suppression. It's been independently tested since 2008 for lithium-ion battery fires. It's kind of become the agent of choice for that particular class of fire with a lot of the battery manufacturers and users out there. And then the last thing you'll see here is the flammable liquid spill control agent. The agent's actually listed on the U.S. Environmental Protection Agency's National Contingency Plan as a surface washing agent. So it can be used to encapsulate and treat hydrocarbon spills on the ground, encapsulate those fuels, and help speed up bioremediation. So we're going to have here is a quick animation that kind of goes over what an encapsulator agent is and what happens when it mixes with water.
Encapsulator technology. The next generation of fire and hazard mitigation. First, we start with a simplified version of a single encapsulator agent molecule consisting of a hydrophilic polar head which loves water, dissolves in water, and a hydrophobic nonpolar tail which fears water and will do anything to get away from water. Once the EA molecules enter the water, they instantaneously and automatically orient with the nonpolar tails inward and the polar heads outward, forming millions of spherical micelles. Micelles travel towards and exit the nozzles, forming EA droplets. Micelles nearest to the surface of each droplet automatically break apart. The nonpolar tails orient outside the droplet with polar heads on the surface, forming an EA skin on the surface of every droplet. In addition to the EA skin, there are millions of molecular spherical micelles within each droplet.
So this orientation of the agent, both on the water and within the water droplet, is what makes it as efficient as it is. Not really changing the physics of water, but we're actually changing the substance. So you no longer have a water droplet, you now have an encapsulator agent solution droplet. The skin on the surface helps to absorb the heat and transfer that heat energy to those micelles within the water droplet, as well as encapsulating and doing some of the other things that the agent can do that we'll get into as we go further into the present. So let's look at fire suppression mechanics and currently how we're operating, putting out fires in today's world. So we know basic fire chemistry, the fire tetrahedron from Essentials of Firefighting, that we need to remove one leg of that tetrahedron to suppress the fire. So if we're using water as a main fire suppressant agent, we're down here working on this heat leg, trying to reduce the heat. We generate some steam, which can help displace oxygen, but primarily we're working on that heat leg, trying to cool the material below its ignition temperature, below its off-gassing temperature to suppress the fire. If we're using a foam type product, be Class A, Class B, we're trying to form that blanket here, separating the fuel from the oxygen on a chemical, molecular, on a mechanical level, forming that blanket, smothering the fire goes out. If we're using a dry chemical, an ABC extinguisher, we're working on this chemical chain reaction here, breaking the chemical chain reaction to suppress the fire. Each of those, all great fire suppressions agents in and among themselves, but they're generally working on one leg of the fire tetrahedron at a time to put the fire out. When we're talking about an encapsulating agent, we have rapid and permanent heat reduction from over 1,000 degrees, well over 1,000 degrees to below 100 degrees in a matter of seconds. So we're removing the heat. We have encapsulation of those fuels inside those spherical micelles, separating the fuel from the oxygen on that chemical molecular level, reducing the toxins and improving visibility. And we've got some testing that we'll see a little later on from testing that's been done at Clemson University, that we can actually interrupt the free radical chain reaction as well. So as opposed to depending on working on one leg of the fire tetrahedron to suppress the fire, we're working on multiple legs simultaneously, working on the entire tetrahedron to try and put that fire out. So we'll get into the actual unique features of the agent. Excuse me. The first one is that rapid cooling. As I said, those molecules on the surface, those F500 molecules on the surface, they work like a heat sink, rapidly absorbing the heat and transferring that heat energy to those micelles within the water droplet. I think a really good video here that drives that point home. We'll speed it up here a little bit. This is actually a video of a thermal imaging video of a vehicle fire. So as you can see, we have a pretty well-involved vehicle fire. Temperatures getting up there in excess of 1,200 degrees C. Firefighter, you'll see the shadow of the firefighter coming in frame here in a second. He's going to be using our TKO nozzle, a 20-gallon per minute nozzle, to rapidly extinguish and cool this fire. So again, a 20-gallon per minute flow, so a very low flow. As you can see, he's not constantly flowing that nozzle. He's using it in bursts. Maybe so far has flown maybe 10 gallons of a 1% solution of F500 onto this fire. You can see the rapid drop in temperature, how quickly that heat is removed, how rapidly the fire goes out. As firefighter opens up the doors, you'll actually see inside the vehicle. Very little heat remains. He'll hit it one more time. And you can see pretty much everything in the vehicle is below 25C. So that next unique feature is the encapsulation. We do that. The way that is tested is through NFPA section 18A, section 7.7, the spherical micelle stability test is how we test the agent for that encapsulation in fuels. That test is this spherical micelle stability test here, that 1:8:40 ratio, plus the kinetic energy of the water leaving the hose stream. So 1 part F500 to 8 parts fuel, the 40 parts water, that when you mix those three together with that kinetic energy from the hose stream, that fuel was actually encapsulated, bound up inside that spherical micelle, rendering the fuel non-flammable, non-explosive. The next part is the reduction in toxins, including hydrogen fluoride, particularly when we're talking about lithium-ion batteries. The agent is able to do that because of two actual features. One is that cooling capability. So we know from fire behavior that as the heat energy of the fire increases, the free radicals that are normally in the atmosphere, that heat energy from the fire starts speeding those free radicals up. Those free radicals collide together, forming smoke and toxins. So F500 has a twofold interaction with that coalescence of those free radicals to form soot and toxins. One is we can rapidly cool the atmosphere, which starts to slow those free radicals back down. So we start to steal some of their energy by cooling the atmosphere. Second, the F500 molecule was a much denser molecule than plain water would be. So plain water, the molecular weight of water is about 18 grams a mole. The molecular weight of F500 is greater than 1,000 grams per mole. So it's a much heavier, much denser molecule. Generally, when I'm talking about this in a classroom type setting where you can see me, we'll throw us out here. If Hernan and I were sitting across from one another and we were in a regular atmosphere and I was throwing a ball at Hernan, he and I could play catch and throw the ball back and forth to each other faster and faster because the air that we're breathing isn't a very dense substance. So the ball easily moves through that air. But if we then went underneath water inside of a swimming pool and I attempted to throw the ball to Hernan, the ball would go maybe a foot and fall to the ground because the water is so much denser than air, it just stops that ball from traveling through it. Same principle with the free radicals. With the density of the F500 molecule, the molecule hits it and it stops, almost like throwing it into a mattress. It doesn't have the ability to travel through that F500 molecule because of the density and it being packed together inside those spherical micelles, just literally grabs onto that. So the testing that they did, that they proved this, they were burning toluene and they were treating the smoke, not the fire, just the smoke with both water and a 3% solution of F500. And they were looking for things like light transmittance. So what was the opacity of the smoke? They were looking for the soot accumulation inside of that inverted funnel, the plenum that the material was burning underneath, and how much soot accumulated inside of there. And then they were looking at the toxicity of that soot and smoke that they collected. What they found after those test results, the comparative test results, that when the F500 was used, there was a 68% increase in visibility, a 97% reduction in soot in the byproducts of combustion, and a 98.6% reduction in soot toxicity. And this information this is from that Clemson study, and you can see here that this information, along with vapor reduction experiments, suggest an interruption of that vapor phase combustion, inhibiting the radical coalescence into soot particles. And generally when I'm doing a class and I talk about that, and everybody's eyes kind of glaze over, because I'm not picking on firefighters, again, 37 years in the fire service, but there aren't too many of us that are chemists. They're out there, especially the hazmat guys, but not too many of us. So I think a really good video that kind of drives that point home to what does that interruption of vapor phase combustion mean, and that stopping the radical coalescence into soot particles. So you have these burning tires, heavy black soot-laden smoke coming off of the tires. We're using 1% F500. And though the tires are still burning, where's that heavy black toxic soot-laden smoke? The smoke's gone. That's the interruption of vapor phase combustion. It stops the soot and those toxins from forming in the smoke. So you have the ability to actually scrub the atmosphere and make the atmosphere safer. Less soot, less toxins, less exposure to those soot and those toxins that we're really concerned about in the fire service right now. So now that we know a little bit about encapsulating agents and some of their abilities, let's look at what they can do for us in each of the classes of fires that we're going to face. So this first one here, typical Class A fires, we have everything here from a structure fire to a vehicle fire. This is actually came from us from one of our fire departments up in Connecticut. That was a combine out in the field that was burning. So again, the types of fires we're talking about: structure fires, vehicle fires, dumpsters, recycling, maybe tires, metals, those types of things. Deep-seated fires, being in silos or in hay, straw or hay, possibly packed paper at a recycling center, those type of things. So isn't the same video we saw earlier with the thermal imaging, but again, another fire. This is from our distributors over in Europe. Again, we're going to be using that 20 gallon per minute nozzle, so a very low flow nozzle. As you'll see, great fire suppression, very little runoff, very little environmental impact. Same way, just like we saw with the tires. Watch that heavy black smoke. As soon as they start applying on the fire, how rapidly that heavy black toxic soot-laden smoke disappears. Again, as we saw, another great application technique with F500, you don't need to constantly flow that nozzle. Normally flooding that vehicle with either water or whatever you're using. Quick applications, get a general knockdown of the fire, and then kind of going in and do an overhaul, just looking at the hot spots. But as you see, we're trying to be as eco-friendly as we can here. Put the fire out as rapidly as we can, using the least amount of solution that we can, creating the least amount of runoff that we can. So at this point, he's just trying to cool the vehicle down, stop a lot of that off-gassing that's going on by cooling off whatever is left inside the vehicle. As you see from the bottle, that's a 2-liter bottle on the base of the nozzle. Very little solution is used, and that vehicle is now cool enough that you can actually touch it barehanded. That vehicle that was just involved with. Another great video here that kind of sends the point home of what F500 can do with driving down those temperatures. This particularly in a structure fire environment. So this was some training I was doing up in Maumee, Ohio, at the Maumee Fire.
All right, so let's open it up.
We were
and
pre-mixed
check
at a
this out.
0.5% inside the booster tank of the engine. This daytime burn, we're using a smooth bore nozzle. So 1.75 inch hand line with a smooth bore nozzle. We're checking temperatures now with the thermal imaging camera.
1200 at the base of the fire, 1000 at the ceiling.
So we had 1,200 degree temperatures at the base of the fire and 1,000 degrees at the ceiling. So we had there a 6 or 7 second flow of the agent.
1200 at the base, 250 at the ceiling.
So we went from 1,200 to 400 at the base of the fire, 1,000 to 250 at the ceiling. Now that was with a smooth bore. So the agent works better with a finer droplet than it does that smooth bore stream. Droplet you can get, the more encapsulation, the more cooling that happens. So we did some additional burns in the evening. This time, excuse me, the same 0.5% solution that we were pre-mixed in their engine with. The only difference this time is we're using a combination nozzle as opposed to that smooth bore nozzle.
You want to go? You want to hit it, Ron?
See that lower stuff doesn't look like it's burning.
No. That's stuff that from this morning.
So if we can, I'll turn my volume up here to hopefully you guys can hear this a little better. They're actually talking about the material at the base of the fire isn't burning like it was in the morning because it was pre-treated earlier with that.
Not burning. About 230 at the bottom and 930 at the top.
So
I got 975 and I was inside.
if you remember in the morning, we had 1,200 degree temperatures at the base of the fire. Now it's about 230 degrees. We've got ceiling temperatures of just under 1,000, ceiling about 937.
470.
So we're now 113 degrees where we were 1,000, almost 1,000, 900 plus degrees to 113 degrees.
Hot, hot. What's the temperature in the hallway right now?
77.
So 77 degree ambient temperature right outside the fire room from the exterior. You'll see
120 ambient in the hallway.
the firefighter comes out, he's got 120 degree ambient temperature at the ceiling in the hallway.
95 at the ceiling.
So as we see, again, rapid cooling,
195 at the ceiling.
rapid suppression of the fire. This particular fire, these are some videos and some pictures that were shared with us by our distributor down in Panama. This was a fire they had this past February of 21 at a tire recycling facility. So as you can see, that heavy black smoke coming off of the burning rubber, just like we saw earlier with the burning tires, the couple burning tires we showed earlier with the demo. So here we go from demo applications to actual live fire applications. They have quite a few fires at this facility, so this isn't I would say a rare occurrence for them. The only difference between this fire and previous fires at this facility is this time they have 100 on board. You can see here another video, just a different angle. Again, as the fire department's getting ready to come up, you know, that heavy black smoke. Now here we are on scene using the F500. Again, as you can see, it's already been applied to some of that area, but that heavy black smoke that generally would be coming off of those tires is no longer coming off of those tires. It's helping stopping the reducing those toxins and that heavy soot that normally would be coming off of those burning tires. Same way here. It's just a couple different videos showing some of the different applications as the firefighters were moving around the piles, extinguishing the rubber chip. So the part that was really interesting about this fire is the information we got from the fire chief after the fact, when they looked at what historically they have had to do at this facility when they had fires compared to what they did now when they had the F500. So in years past, previous incidents, it took 40 plus hours to get that fire extinguished. So they were on scene, day and a half, 2 days to get the fire out. They generally use 2 separate apparatus, 5 firefighters total, and just estimating maybe 60,000 gallons of plain water they used to actually get that fire extinguished. This past incident where they had the F500, they were applying F500 at 1%. They had the fire extinguished under control in 2 hours with the use of 1 apparatus, only 2 firefighters on that apparatus, and they figured they used about 3,000 gallons of a 1% solution to actually extinguish that fire. So if we're looking at that environmental impact, if we're looking at rural firefighting where most of these facilities are located, where we have to set up tanker shuttles and bring all that water in, where you may be able to extinguish that fire with a single tanker instead of having a 2-day tanker shuttle, bringing your water in and out, 40 plus hours to extinguish with 2 apparatus. You have 80 hours of engine time on those 2 apparatus, as opposed to a total of 4 hours operating time on that apparatus. It's not only a game changer in safety, but some of the pushback I get when I'm talking with the fire service is, everything has a cost. And, you are correct. There is a cost associated with F500 like there is any agent. But when you look at the savings you can have in both man hours, apparatus wear and tear, the safety factor of just being on that scene that long with wear and tear on your manpower and your equipment, the agent actually, I feel, saves you money. Even though you're spending money, in the long run, you're actually saving money. Some of the wildfire applications, credit to Hernan, a lot of this comes from the work he did in the past few years down in South America with the fires down in the Amazon. That's where all this is from. So this first one here is a test burn they did when Hernan was trying to, again, kind of like we're doing now, but COVID wasn't in place, so we could actually go out and work with folks. They pre-treated the back half of this burn pile and then did a run. So the F500 not only works as a fire suppressant, but it works as a retardant when you can get it ahead of the fire. So it's ideal for that wildfire application because you can suppress the fire and you can also stop the spread of the fire with the agent working as a retardant.
Fíjense cómo paró, lo paró. Ya no avanza, se enfrió.
So as we sit here, we'll kind of speed along through the video. The F500 here still on the ground, but again, you can actually create a fire break with the F500, even with that dry, very dry, flammable tinder type material. So again, kind of like we saw earlier with some of the other, That was some testing that was done. This is for the Spanish folks that are listening. Everybody else is going to have to read. This is actually news footage.
Hazard Control Technologies
Some of
presents
the
F500
applications of
encapsulator
F500
technology.
during the wildfires down in the Amazon.
De martes se llevó adelante el primer operativo con el agente encapsulador en San Fermín. Es decir, con la aplicación de este agente químico se logró controlar el incendio en esta comunidad.
En este sector que ustedes han visto, sí. ¿No? Ahorita ya no hay focos de calor, se ha liquidado bien.
El agente encapsulador ha pasado la primera prueba. En la entrada hacia la comunidad de San Fermín se ha logrado controlar este incendio, lo cual ha causado satisfacción en los bomberos y también en el personal de la gobernación, que han visto la rapidez con la que se actúa y luego se liquida todo el incendio.
El primer foco de calor que apagamos con esta agente encapsulador, como vemos hasta se siente otro olor, no el olor normal. Lo tocamos, fíjense, la zona, tocamos y ya está prácticamente fría. Tenemos al medio de donde se ha aperturado el fuego una cisterna con 10.000 litros de este producto.
Se nota que tiene una efectividad elevada, ha bajado mucho la temperatura, el trabajo ha sido corto el nuestro de liquidación, pero dentro del proceso de extinción está la extinción, la liquidación y el control. Vamos a permanecer en el área unas cuantas horas para el control y evitar que esto reinicie. Lo más desgastante es usar una mochila, ir, volver, son distancias largas. Son 4 veces menos que vamos a hacer este trabajo y lógicamente vamos a maximizar la fuerza de trabajo de la persona adentro y por ende también vamos a ayudar a que esto no se reinicie. Y vamos a dotar a las mochilas para poder acceder, monte adentro y lo que nos encontremos en el camino o en las propiedades lo vamos a usar con el vehículo de intervención.
Y la aplicación de este agente encapsulador es supervisado por un bombero argentino que es representante de la empresa proveedora.
Y la idea es con ellos ver la aplicación correcta. Es un producto que enfría entre 3 a 5 veces más rápido que el agua. Encapsula mejor el humo, ustedes lo van a sentir que el olor es diferente, como si fuera un olor de un detergente. Vemos el tema de que va a ayudar con respecto a lo que es la intoxicación tanto de los bomberos como de los habitantes locales. No tiene flúor, es medioambientalmente muy bueno. Queda en la tierra un par de días para evitar que se vuelva a prender. La idea de esta primera parte es mojar todo lo que se pueda. Todo lo que vos venís atacando, lo liquidás, no es que lo dejes herido al incendio, que te vas a otro lado y eso se vuelve a reiniciar mañana, pasado eso. Trabajo coordinado, termino, liquido, avanzo al próximo. Cuando empieza el fuego intenso, se ataca con una unidad un poquito más grande. Cuando se baja la intensidad, se entra el resto de las personas para poder liquidarlo finalmente. Esto ya está liquidado, está en los últimos momentos. Lo que ustedes van a ver que está humeando está dentro del área quemada, que no tiene riesgo de propagación.
So that video kind of covered, the ground-based attack. Here's another one. The agent can be used both and aerial-based. You're going to see here an airdrop coming in.
This video, it was in Córdoba, Argentina, Ron.
Okay, so the first one, the hand application, was in Bolivia. That airdrop there was actually in Argentina at a wildfire in Argentina. So again, multiple locations. Hernan actually got it being used in multiple countries in South America on the wildfires that they've been struggling with down there, just like we are here in the States. So let's look at some of those Class B applications where you can use the agent. Things like gasoline, ethanols, diesel fuels, oils. This one here is a test burn I was doing at a fire academy just outside of Pittsburgh. So this is EA.
Ron, can you repeat, because
Yes.
with the sound of the video, we don't listen you.
I'm trying. I lowered my go, Hernan. I figured that would affect it there, but
No, but you can explain what is in the video now.
okay. Let's see if this works. So if
Okay.
you know. Okay. So this is a diesel fire. So this is diesel fuel training we do down at the Public Safety Training Center. So probably about 40 gallons of diesel fuel, 25-foot pit. Again, 3% solution of F500, 125 gallon per minute hand line. Again, sweeping back and forth across the surface of the fire, encapsulating those vapors that are off-gassing while we're cooling the surrounding structures and all those impingements that are inside the pit. So let's look at, so those were some two-dimensional applications for F500 for an encapsulating agent on Class B fuels. Now let's look at some of those three-dimensional applications. So the first thing is, a lot of folks will ask, what is a three-dimensional fire? So it's burning fuel that spills or cascades from a higher plane to a lower plane or a lower altitude is considered a three-dimensional fire. So some examples of that are things like a tanker truck where you may have this side of the tank is split open, a wellhead fire that we've had a few of them here in Western PA with a lot of the Marcellus shale drilling that's going on, distillation column at a refinery or at a plant like that. And if we look at still in a lot of those applications, folks are still trying to use foam to suppress fires because it is a flammable liquid. Everybody knows Class B foams you use on flammable liquid fires. But if we look right inside the NFPA 11 standard that covers both hydrocarbons and foams, it tells you foam is not suitable for three-dimensional flowing liquid fuel fires or for gas fires. So we do use it and we try and use it in those applications. But a lot of times in that application, the foam's actually not a really good solution for that type of fire. So we have over in China some testing that was done over there on a distillation column. This one's actually going to be spraying gasoline. So it's a pressurized three-dimensional flowing fire of gasoline. Again, 3% solution, single hand line. So we see this a lot where the fire departments are setting up just trying to cool the tower, because they know they don't really have the ability to suppress that fire. They're trying to keep it from spreading. Well, with F500, you have the ability to actually rapidly suppress that fire. Next one, it comes from us, from our Vietnamese distributor. They actually built a tank truck simulator. So this is a fuel truck. Actually pumping a combination of diesel and gasoline off the top of the truck and having that fuel run down the side of the truck and create a pool fire underneath the truck. So a three-dimensional flowing fuel fire, something that fire department quite easily could face. You get a tank truck where it's the tires, you get a hot break and it catches the tires on fire. The tires end up spreading to the fuel tank. And this is what we see when we roll up. You have a fuel running on the ground, catching the underbelly of the truck on fire, as well as the vehicle itself and the tank that's containing the fuel. They're actually going to attack this fire using 2 hand lines. The hand line on the front actually has a very fine mist rotating fog nozzle. It sets out a very fine, widely dispersed pattern of encapsulating agent solution. The rear side of the tank, they're just using a standard combination nozzle. Again, they get a nice pre-burn on the tank. They get everything good and hot, which is it. That's your problem with these types of fires, that steel gets so superheated. It's really hard to get that material, that steel, that structure of the truck cool enough to get it below the auto ignition temperature of the fuel, where you may have some success on the fuel itself, but the truck is so hot, it just keeps reigniting the fuel. Something to notice here when we talk about the radiant heat that you can imagine is coming off of this fire. Again, they don't have the best equipment over in Vietnam. The firefighter on the front with that dispersed rotating fog nozzle doesn't have gloves on. So you can imagine what the radiant heat would feel like. But again, the agent is really good at just absorbing that heat and taking that radiant heat away. So as you can see, they're just working their way around the tank. Right now, he has the fire out. He's just continuing to cool that tank now. So now they're applying the agent onto the tank, that solution, to take that heat out of the tank. They're trying to cool the tank while they're encapsulating the fuel that's still running out of the tank to make sure it's not going to reignite because the tank is so hot. So next application, Class D type fires. Things like magnesium, which we're finding more and more in vehicles and in tools today. I think the last I heard at a webinar I was on, they were talking about excuse me, Class D metals in a modern vehicle, and it's somewhere up in excess of 250 pounds of Class D metals inside of a modern vehicle. Titanium, again, is being used in vehicles, also in some tools, sporting equipment. And then you have the zirconium, which a lot of times is being used in combinations with other Class D metals to make specific alloys. So this is a video from, stole this off of YouTube. This is LA County fire. And this is what can happen when we use the wrong application on a Class D metal fire. So this is at a metal recycler, again, out in California. They were working with titanium. I know the safety manager for this company personally, and he told me when the fire department initially got there, you know, their plant people were telling them, this is a Class D metal, it's water reactive, don't use water. And again, not picking on the fire service, but, you know, I can speak from experience. We're the firefighters. We think we know best who to tell us how to put a fire out, you know. So they're doing what fire departments do. They're brought in hand lines and they're fighting the fire. So as you can see, they're flowing some, in some cases, larger streams, 2.5-inch lines, 1.5-inch lines on those fires on that burning titanium. And you're going to see here pretty quickly, it's going to get bad in a hurry on these guys. So they're talking about repositioning. And what we just had there was a Class D metal explosion. So that titanium reacted with the water that was being put on it, and you had that massive explosion. That actually sent 6 of those gentlemen to the hospital. So they sent 6 firefighters to the hospital due to that explosion at that facility. This is some testing I did with that same company that owned that facility in Los Angeles. This is at their facility in Columbus. We're actually doing some test burns. They were looking at the F500 fire extinguisher. This is a titanium zirconium mixture here. So as you can see, rapid fire suppression, no reactions. Very little solution used. We maybe used a gallon out of that 2.5 gallon extinguisher to extinguish that. So again, rapid cooling, extinguishing of that fire without any of the reactions you see with a Class D metal. This is actually a magnesium application. So video's a little older, but this was actually up in Canada. This is a lawnmower deck. It's a lawn boy mower deck, which is, if anybody remembers the old lawn boy lawnmowers, they had a magnesium mower deck. That's what that is a burning magnesium lawnmower deck. So not chips like we had previously, but this is solid magnesium. Not shavings, not fines, but actually a solid. So you're seeing here the application technique, kind of like we had with that water mist extinguisher. With a Class D metal, we want to use a dispersed pattern. We want to start by kind of raining down on top of that Class D metal, start to pull some of the heat out. Again, if we remember, those micelles were rapidly absorbing the heat, transferring that heat energy to the solution, to those micelles within the solution. As you can see now, we've got it cooled from that burning white hot to more of an orange. He's now using a more direct application to finish suppression of that fire. We've now cooled the magnesium enough that even if by chance the F500 would get knocked off the water droplet, that F500 skin would get exposed. The magnesium's now burning cool enough that it's not going to interact. It's not going to split that water into hydrogen and oxygen. In fact, that material's cool enough now, if you saw the firefighter took his glove off, and he's able to barehanded carry that magnesium lawnmower deck over for everybody to look at. So again, something from burning in excess of 5,000 degrees to handling it by bare hand a minute later. So again, rapid cooling. That's why it's so effective on those Class D metal applications. Let's look now at to me, the truly up and coming hazard. So we've had solutions for most of the other fires that we've covered already, be it water, be it foams. You know, we have some other, the dry chem extinguishers for use on Class D metals, but there really isn't a good solution for lithium ion batteries. And this is the up and coming hazard that, face it, this is what we're reverting to, be it electric vehicles, be it consumer products, aircrafts. They're talking both boats and potentially helicopters that are fully lithium ion battery powered. You know, like I said, the cars, consumer electronics, your kids' toys, they're everywhere. You know, and the results sometimes can be catastrophic because I think there's a misconception that the batteries generally fail if they're abused. Yeah, if you abuse a lithium ion battery, you increase the chances failing, but they can also fail just because it's a defective battery and you have a short circuit. This is a lithium ion battery powered forklift. And again, as you see, pretty serious malfunction that the battery just, for the most part, spontaneously combusted. This is as you can tell, a factory setting. You know, the most common fire suppression in a factory is your generalized ABC fire extinguisher. That's what code requires. So you'll see these plant employees are going to come up and attempt to fight this fire using their ABC fire extinguisher. So the first gentleman there is attacking the fire from the right. You're going to see the whole rest of the crew coming in, including the gentleman there that missed fire extinguisher training because he discharged about 20 feet too soon. All told, I think I count 6 or 7 extinguishers they're using trying to put this fire out. And currently, it looks like they're making some pretty good headway, but all they're really doing is suppressing the Class A materials that are burning on that forklift. They're doing nothing to pull the heat out of that lithium-ion battery, which is what you need to do to actually suppress that fire. Another cell ruptures within that battery. Everybody kind of scampers off because it's a large fire. And then unfortunately, the forklift continues to roll off through, excuse me, the factory, potentially spreading that fire. So some testing that was done here. This is video of testing that was done in combination with our European subsidiary, HCT Europe, and Johnson Controls over in Europe, a company called Norapine, which is a fire extinguisher manufacturer that's owned by Johnson Controls. Norapine was looking to sell F500 extinguishers to Tesla, but Tesla required some third-party verification that the extinguisher was actually going to be effective and do what they wanted it to do for the lithium-ion batteries. So this was multiple days of testing at a third-party testing agency, Kiowa, over in the Netherlands, where they tested dry chemical and foam extinguishers that were manufactured by Norapine and Johnson Controls, and also the F500 fire extinguisher. So they have identically sized lithium-ion batteries that they're heating to thermal runaway. These were fully charged batteries that they took into a thermal runaway event and then attempted to extinguish each of the batteries with various extinguishers. So kind of the same thing you're going to see here with the dry chemical that we saw with that forklift fire, where it's literally, it can do nothing to remove heat from that lithium-ion battery, which is how you extinguish a lithium-ion battery, is to cool it to stop that thermal runaway, and you can't cool with a dry powder. The foam extinguishers, this testing actually showed that some of the foam products were actually having an interaction with the electrolyte, the flammable electrolyte in the battery. So that wasn't really effective either. But as you can see, kind of like the same thing we saw with the vehicle fires, not a constant application, but just the short bursts of the F500 solution, rapidly extinguishing that battery, rapidly cooling that battery off. So these particular batteries are made up, these are cell structured batteries. So they're made up with the 18650 cellular type batteries. So two different kind of, you're mainly two different kind of battery makeups. They're either cellular, individual cell batteries, or they're prismatic polymer pouch batteries, and we've got testing on both. So the results of that testing now been published by Kiowa and also Johnson Controls in their brochures for the F500 fire extinguishers. As you can see, the powder do not apply on a lithium-ion battery fire. The foam extinguishers are not recommended, but the F500 extinguisher can be recommended to apply on a lithium-ion battery fire. Again, this is a video now. This testing is now being done over in Germany. It was more extensive testing that was done. This was done at a technical university, TU Klosthaus, and then again, the Fraunhofer Institute over in Germany. Two different, I compare them here in the US to kind of MIT or RIT. So a highly technical university engineering type thing. They do this type of research. So again, the polymer pouch, they're overcharging it until it goes to thermal runaway. Now, though, they're using remote extinguishment on the lithium-ion batteries. They're not relying on manual fire application. So as you can see with the polymer pouch batteries, you get a much larger initial fire because there is much more of the flammable electrolyte inside the polymer pouch than there is in the individual battery cells. So the reason they went to this remote testing, remote suppression, one was to get a more controlled extinguishment. More importantly, though, is that gentleman from Kiowa that was doing all of the testing there, as you kind of saw in the videos, he wasn't using respiratory protection, and he actually had to spend a few days in the hospital due to hydrogen fluoride poisoning. So they didn't want to expose anybody else to those toxins that are given by the batteries. So that's why they went to this remote setting. Here now we're back to the 18650 cells. This test they actually did in a very controlled environment where they could track the temperatures on the battery. So this is thermocouples set throughout the battery where they could actually track the increase in the temperature of the battery, high definition video feeds, and also a thermal imaging video feed. What else they were able to do with this testing is actually extract the gases and see what was in the gases from these batteries burning. So we'll go ahead and speed this up because this is about a 20-minute video. But as you can see on the graphic, the temperatures are rapidly building on the batteries. So right there on the 7-minute mark, we actually get ignition and we go into thermal runaway. See the temperatures here. So they're going to let that battery burn for another couple minutes. See the individual cells continue to rupture because the heat's being spread. That thermal runaway is continuing on its own. You look, we're 700 C, 500 C, 600. Just watch the temperatures as soon as the agent is applied. Look how rapidly we drop from 600 plus C down to 17 C and below. So again, rapid suppression, rapid cooling of that battery, stopping thermal runaway. So everybody says you can't stop thermal runaway once it starts. You can with F500. We've got the testing to show that you can literally stop thermal runaway. They allow that battery to sit there, then continue to monitor the temperatures. And as you see, we have no heat buildup at all. So when they looked at those gases that were coming off of the batteries, what they found is the batteries burning without being extinguished. And this was for a combination of both the polymer pouch and the cell type batteries, the 18650s. They were giving off anywhere between 227 million or parts per million and over 2,600 parts per million of hydrogen fluoride gas. Hydrogen fluoride gas is highly toxic. The US NIOSH, the National Institutes of Occupational Safety and Health, their IDLH, immediately dangerous to life and health for hydrogen fluoride, is 30 parts per million. And as you see with those batteries burning, just free burning, they were giving off between 227 and over 2,600 parts per million of hydrogen fluoride gas. When the F500 was used to extinguish them, those numbers dropped to anywhere from 37.5 to 1.25 parts per million. So again, a drastic reductions in the toxins that are coming off of those batteries when they're burning. So kind of like we saw earlier, that's some of the testing that was done. These are some photos, and we've got one video here. This is the Moto E circuit over in Austria and Germany. So this is fully electric motorcycle racing. Again, here's the Norapine F500 fire extinguishers that are used. This was actually one of the bikes that caught on fire. As you can see, the F500 solution here on the ground, that they're using the F500 to suppress that fire. The video here is a wreck on the racetrack. And again, you see the response crew out there with the F500 extinguishers actually controlling that fire, cooling that battery, and not even fire. They're mainly cooling the battery, stopping that thermal runaway. So they're cooling the battery before it even gets to thermal runaway, just to ensure that they didn't have a fire that they had to deal with. So the last thing we'll touch here is some of the capabilities that the F500 can give you in hazmat. And again, hats off to Hernan, because a lot of this testing was done while Hernan had to spend some time down in South America in both Argentina and Chile. So things like train derailments, tanker accidents, tanker rollovers, chemical spills, fuel spills, all the things where F500 can give you an advantage where other products either can't or aren't as effective. So these first photos here, this is from a train derailment in Chile. The train was actually carrying tankers of sulfuric acid when it derailed. So we had both the diesel fuel here that was leaking from the engine, as well as sulfuric acid that was leaking from the tank cars. In both cases, they used a 3% solution of F500 to both encapsulate the diesel fuel and take the flammability away from the diesel fuel. And what they found through testing in Chile is using a 3% solution of F500, they could actually neutralize the sulfuric acid, take it to a pH neutral without an exothermic reaction. So it gave them a really good solution for handling these incidents with sulfuric acid. This next one is a tank truck rollover in Argentina. Again, tanker rolled off the highway. The saddle tanks ruptured on the tractor. Diesel fuel all over the ground, and they're using the F500 to actually encapsulate the diesel fuel from the tank truck that had overturned. Here again, another tanker incident in Chile. This was two tank trucks, two over-the-road tankers that ran into each other, again, creating a sulfuric acid leak. Video here, they actually had one hazard came in that was attempting to bury the sulfuric acid, but they weren't being too effective. So they've now diked it to contain the sulfuric acid, and they're treating that spill again with a 3% solution of F500 in order to neutralize that acid. These next ones, this was actually out in Globe, Arizona. So this was a tanker carrying gasoline and diesel that actually rolled, I don't know, looks like 100 feet or more down over an embankment. Didn't have a safe way. The truck was fully loaded, really had no way to get it back up to the highway. So state DEP came in, they set up some remote monitoring, checking for flammable levels, and used the F500 as they were tilting the truck over, spilling, they're tilting the tanker to get rid of the fuel out of the tanker so that they can have the ability to lift the tanker. So they're using the F500 to encapsulate that fuel that's coming out of the tank, keep the LELs down to make it a safe working environment. Again, really no other application, no other agent you can really use in this application. Foam wouldn't be applicable because you can't form a foam blanket over that large three-dimensional tank. Plus the fuel is continuing to run. So you wouldn't have the ability to form a blanket over that. It's a wide open area, so you can't use an inerting gas because there's no way to contain the gas. So really the only viable solution was the F500 to be able to encapsulate those vapors into fuel in order to achieve getting this truck back up onto the highway. Another video here where they're now lifting the truck, the tank's empty, but they're continuing to apply F500 onto the tanker, still making sure we're encapsulating any vapors that may be coming out, treating the soil below the truck, just making sure we don't have any sparks, no flammable vapors that potentially could ignite to injure anyone. So as I said earlier, encapsulator agents give you the ability with one agent to face multiple hazards. So it's nice in the fire service. I try to, again, not picking on firefighters, but my thing is I like to try and make stuff idiot proof or firefighter proof. So, as opposed to determining, do I have a class A fire or a class B fire? Do I have a hydrocarbon fire? Do I have a polar solvent fire? Do I have a class D metal fire? Or do I have a combination technically in a vehicle fire of all three, all four? I could have a hybrid lithium ion battery, E85 gasoline with magnesium, with other class A combustibles all in one fire. How can you handle that? You can't use, some class B, some class D extinguishers, some class B product. F500 gives you the ability to handle all of those different classes of fires with one product. So it's really a great way to expand the capabilities, your fire suppression capabilities, to handle anything that may be thrown at you. So that's kind of the end of the presentation. We can open it up for questions.